Welcome back, everybody. I hope you had a nice start of the week. The topic this week, which is going to be our kind of last lecture week. Next week, we will go through a quick summary, and then we will spend the rest of the time on the project solution and project discussion. So what I wanted to bring up today, after we had these discussions about Boltzmann machines, is how you could actually set up a neural network. And I will also link this up with discussion of codes, which you can find on the website of the course here, the GitHub address. And I'm also going to link to existing software, which you can download and run on your laptops or PC or whatever, and use them to calculate or find the optimal energy using a neural network. So this is basically the kind of motivation for today's lecture. We may not need all 2 hours, but let's see how far we get. Now, to remind you a little bit about what we have done and why we have done this. So you can view today's lecture as more a kind of path towards new things. The implementation of a neural network is something which we have set up as an optional part. This is actually much more it's going to be much more time consuming than implementing the Boltzmann machines. And one of the reasons why we have focused on Boltzmann machines is the pedagogical aspect, which allows us to reuse everything we did in project number 1 and use the Markov chain Monte Carlo machinery. We can then use the Metropolis algorithm, we can use blocking, etc., in order to find the best possible expectation values with their best possible standard deviations. We will then use these Boltzmann machines in the project, and this is the kind of recommended path. And then if you have time, we can then think of, or you can think of, implementing a neural network, but I would not recommend that because that's going to be much more time consuming. But it's something which what I want to do today is to draw and outline the pros and the cons of the different approaches. So as we discussed last week, Boltzmann machines belong to that category of deep learning methods, which are called generative models. So that means that you train a neural network with a probability distribution. And the standard way this is being used, like in many of these deep learning generative algorithms, like ChatGPT, for instance, is based on generative models, is that you actually train a distribution function, and then, or rather the log of the probability distribution which are chosen. And this will depend then on parameters of a neural network. And this can be a deep network, or it can be a shallow one, like a restricted Boltzmann machine, which we are implementing. The benefit which we have is that this probability distribution is used as our trial wave function. And we can then reuse everything we have done. This is the pedagogical axis. On the other hand, this brings you in touch with the very active research field of generative models. And if you wish to, or if you would like to outline where these deep learning methods are going and where there will be a lot of emphasis in the years to come, there's actually been a lot of emphasis already, it will actually be on generative models, where you learn a probability distribution. And this allows us to use the Markov chain Monte Carlo machinery. And for those of you who are familiar with neural networks, this means also that we do not implement in general. We can do that, but we do not implement what's called the backpropagation algorithm. And all the hassles we have with setting up all the derivatives and backpropagate and calculate gradients, etc., etc. The thing which we, however, will do, irrespective of whether we implement a Boltzmann machine or whether we implement a neural network, is that we need to take the derivative of this function here. And I wrote the expectation value, the local energy, in this kind of more sloppy physicist way of writing an expectation value. So when we do the Boltzmann distribution, we actually optimize the expectation value of the energy, which then depends on the parameters that define the Boltzmann distribution. And this is typically where you deviate from what is common in machine learning. So rather than defining a cost function, however, rather than defining a cost function, which is based on some data set, our cost function is now the energy of the quantum mechanical system. And this is the quantity we want to optimize. And if we minimize the energy, we know that this should lead to the ground state wave function. So irrespective of whether we use Boltzmann machines or neural networks, this is the function we have to optimize. So just keep that in mind. So there are commonalities between you setting up a neural network, a standard feed-forward neural network with back propagation, etc. And for those of you who have taken a course in machine learning, which is a good fraction of you, the back propagation algorithm is the way you implement the training process through the calculation of the gradients. So this is more to give you a kind of bird's view on what we are doing. And the quantity which we need to calculate at the end is this quantity here, which is the gradient of the energy, the expectation value of the energy of this local energy operator, which we have defined. And these parameters theta, they are the biases and weights of a neural network. So when I say neural network, it's going to be generic for either a Boltzmann type machine or a standard feed-forward neural network, or it can be a convolution neural network, recurrent neural network, or any type of the neural network-based models. I'm going to come back a little bit to the way you set up a neural network when we are going to dive into the more details of setting up a neural network. Now, for the non-interacting case, we have this code, which you will find also in the Jupyter notebook, which is the one we have been discussing. And that can serve as an example for how you should set up the trial wave function. And we discussed these details last week, and you have that, these details, all the details you need to program, you have those in this lecture slides from last week with all expressions. And the code, which you will find then, simply includes all these expressions which have been coded. So let me quickly remind you of that. So I'm going to switch back to my Jupyter notebook. So let me do that. So this is just a quick reminder of what we did last week. And what we had then was a neural network code for a Boltzmann machine, where we then implemented the non-interacting case. There is an option for the interacting case, where we used a Gaussian binary energy expression. So the Boltzmann machine has a Boltzmann probability distribution, which then is given by the exponential of -1 multiplied with the energy function. And this energy function is where we bake in all the parameters of the neural network. So in this specific case, without bringing back all the details, we are setting up a trial wave function, which is given by the Boltzmann distribution, and where we're setting up the positions of the different particles. So A, B, and W are the parameters theta. So A are the biases for the visible nodes, B are the biases for the hidden nodes, and W are the weights for the connection between the visible nodes and the hidden nodes. And these are variational parameters, or in the deep learning literature, this would just be called training parameters. And then when you optimize this function by minimizing the energy, you will find then the optimal parameters A, B, and W. And in this specific case, I'm now setting up the local energy with this new wave function. So we sum over the hidden nodes. Sorry, this is allergy season. And there's also an option if you want to plug in the interaction piece. There is a derivative of the trial wave function, which is given by the Boltzmann machine. And we went through the equations last week and the week before. and similarly with the quantum force. So these would be the pieces which you would need to change in your old code from project number 1. The rest, the energy minimization, is a standard Markov chain Monte Carlo, where you loop over the parameters you have. You have a loop over the number of particles, you set up the initial positions, etc., and then you have the loop over Monte Carlo cycles. And the way I set it up is so that I actually defined a function which also computes the derivatives of the wave function in the same function. So that means that the same function calculates the expectation value of the energy, but it calculates also the expression for the derivatives. And this is something which we went through in more details in connection with project number 1. So just to remind you, if we just go up again, the expression which we have here, this number 2 here, is the same as we had in project number 1, except that now we are going to have more parameters. But in essence, if you have set up an expression and a code for this, you can then just change this to the new type of wave functions. And that's one of the reasons, and you see clearly one of the pedagogical reasons why we use Boltzmann machines. Boltzmann machines, another reason is that they have been extremely popular for Hamiltonians which involve interactions between spins. I don't know how much familiar you are with that, but there is a whole field in theoretical condensed matter physics where one has dealt with the spin-spin interactions, and there are some famous Hamiltonian like the Heisenberg model. You have most likely met the Ising model. There's a quantum mechanical variant of that. And these are all models which then take only binary values. I mean, you have a spin up and a spin down. So the binary Boltzmann machine, which we discussed last week and the week before, is actually a very interesting model for implementing these type of Hamiltonians. So these type of Hamiltonians, which have been extremely popular in solid state or condensed matter theory, are Hamiltonians which are approximations to real physical Hamiltonians, because there are no spatial degrees of freedom. So we are dealing both with the spin and the spatial degrees of freedom, which means that our Hamiltonian is a little bit more complicated with respect to those. And that's why we included this Gaussian binary Boltzmann machine, where we have a continuous input variable, which then is going to represent the position of the particles, which enters the argument as an argument to the trial wave function. Feel free to stop me and ask questions. So this code which you have here is a code which runs through the non-interacting case first for only 2 particles. And it obviously depends on the energies which we are dealing with. It depends on learning rate, which we have defined to 10 to the minus 3 here. I put only 50 iterations. And this is meant mostly for pedagogical purposes. And in this case, I set up the derivatives now, which are then related to both the gradients due to the biases and the weights themselves. And then I update the gradients here. And these are the quantities which then enter the definition of the derivatives and the optimal parameters. So the gradient is the quantity we want to drive to 0 in the optimization process. And at the end, we will then have a set of parameters A, B, and W, which are the optimal representations of the wave function. For the non-interacting case, this Gaussian binary Boltzmann machine does a pretty good job, and we are essentially almost spot on the theoretical result. Now, there is a printout here, which I haven't been using. You don't need to look at this one. Yeah. So if we now go, so this was about the setup of Boltzmann machines. Let's now go back to the slides themselves and look at the calculation of a neural network here. So when we are going to develop a code for a neural network, and the way we will implement that or can implement it is a little bit more difficult. So what we have seen is that these Boltzmann machines are pretty straightforward to implement. But due to the ansatz which we've made for this energy function, so the standard one for the case we have in the project number 2 would be a Gaussian binary. This can be implemented with analytical expressions for the probabilities which we're needing, and then thereby the trial wave function. However, these energy functions, as soon as we move a little bit away and introduce a more complicated trial wave function, it's not given that the Boltzmann machine will capture the physics of the system. And you have probably seen that when you run with the interaction piece, when you add this, either the Coulomb interaction or the interaction from project 1. If you run for project number 1 with the same interaction, this interaction is pretty weak, which means that you will not be so far away from a Gaussian binary Boltzmann machine for the trial wave function. Now, you can multiply your trial wave function with, so that means the Boltzmann machine in this case, with the functions which include more physics information, and that will often bring you to a better result compared with the other standard methods like variational Monte Carlo calculation. So the problem now, as you can see here, when you want to compute the so-called marginal probability, which defines the wave function for you, that becomes extremely complicated if you have more complicated probability distributions. And this is one of the reasons why Boltzmann machines, except for this case with the spin-spin Hamiltonian, has, how to say, the interest in them has been a little bit lost. And neural networks have actually taken over here. So neural networks, they offer actually much more flexibility. And the price we have to pay is, however, an additional computational cost due to the many more parameters which are needed to train and the implementation of the backpropagation algorithm. And thereby, normally, this is done with automatic differentiation. So automatic differentiation in reverse mode. So automatic differentiation has actually two modes. There's a forward mode and a reverse mode. And for those of you who have taken the course on machine learning, you've already gotten familiar with what this means. And the backpropagation is actually a way to set up the training of a neural network by finding a recipe for the gradients at every stage, which means at every type of hidden layer. You can then find expressions for the gradients and the unknown parameters for a given hidden layer. So the drawback now, even if we are going to use the same function, this is our gradient. Now the parameters will depend on a given layer where you are, but still the function you want to optimize is the energy, and that means that you have to calculate the gradients, and these are the gradients which you need to set up. Now so this means that you need now to set up the backpropagation algorithm and automatic differentiation. This can actually be done with a software like TensorFlow. In the examples in the codes which you will find, in which you have access to, I'm coming back to these codes. There is a standard two-body problem for a gas of fermions in 3 dimensions. And it's normally modeled by some non-relativistic Hamiltonian where you have kinetic energy, you may have some additional potential, plus a two-body interaction. But in general, you can then add a external potential like the harmonic oscillator, which we had in project number 1 and also in this project. Alternatively, you can play around with different potentials here. So one could be the Coulomb interaction, which you're looking at. It could be the interaction from project number 1. There is another potential which is actually very popular, and this is called the Purcell-Teller interaction. And it's given by this form here, and it has been used in widely in quantum Monte Carlo calculations, QMC here. And this is a spin system which acts only on systems with opposite pairs. So that means that particle 1 must have spin down and the other must have spin up, or -1 and +1. And then we have the spatial degrees of freedom, which are given by this Ri, and then the spin projection on the z-axis of a given particle. And this V0 and mu are just parameters. The nice thing with this Hamiltonian here, it has analytical solutions. And that's why it has been widely studied in many-body physics. And it provides an analytical solution to the two-body problem. And it's also something which is called the unitary limits that corresponds to the zero energy ground state between two particles, where the unitary limit corresponding to the zero energy, the ground state energy of the particle with given parameters. And this is a system which has also been widely studied in order to see if one can study the phase transition from what is normally called a normal Fermi liquid. So there's a lot of many-body jargon here. So these are interacting fermions to a system which exhibits a phase transition of the type of a superfluid or superconducting phase transition. So these are types of interactions. Now, when you're modeling this for fermions, so the codes which you will have access to, they're dealing with fermions. And they can obviously be tailored to just 2 electrons or 2 fermions. And that simplifies everything because you don't need, in our specific case, the way we set it up, to take into account the spin degrees of freedom. And the normal ansatz, however, is that you would have a trial wave function. So if you can set up a simulation box with a given number of particles. You can have periodic boundary conditions or other types of boundary conditions. And then you would then define a trial wave function, which now contains a so-called Jastrow factor, which is a positive definite object. So that means that it gives a symmetric contribution to the trial wave function. And then you can have a so-called Slater determinant or Slater-Jastrow type of determinant, where you then would simply have the determinant and where you have chosen a set of single particle states, like we did in project number 1, except that then we studied a system of bosons only, and we didn't need to take into account the anti-symmetry of the wave function. So in the fixed node approximation, which is pretty common, so you actually fix the node of the particles, then you could take the single particle states to be products of spin eigenstates and plane wave orbitals. And this is one possibility if you're looking at a system with continuous variables meant to mimic an infinite system. So you would have a simulation box with a given number of particles, which then defines your density. So the simulation box has a given length. And you know that when you have a simulation box, which is meant to mimic an infinite system, you would have to include some boundary conditions because the particles at the boundary, they will not see as many particles as the particles in the interior of the simulation box. And that leads to a whole field in the simulation of these systems, which deals with boundary conditions. And one of the standard ones is in physics is actually periodic boundary conditions. And there are many techniques which allow us to also modify this nodal structure or the Slater determinant. So these are technicalities which you don't need to deal with when it comes to project number 2. So I am mentioning this so that you can get a kind of bird's overview of how you would implement neural networks. The codes which we have, they deal with fermionic systems, but there's nothing which hinders you to change the basis set and also to add other types of particle wave functions, like single particle wave function, which in our case are essentially given by harmonic oscillator type of wave functions. So in the codes, there is an emphasis on systems which are meant to mimic an infinite system, but there's nothing which hinders you to set up the same machinery for a finite system, where now these functions, instead of having plane waves, are now replaced by, let's say, harmonic oscillator wave functions, or wave functions which are more realistic for, let's say, atomic and molecular physics and quantum chemistry simulations. So the thing you need to feed into the network when you're setting it up. You need to have some kind of information about the symmetries of the system. And that is a very, very important aspect. So typically, and for the project which we have now, you don't need to introduce the spin degrees of freedom, because we can skip spin degrees of freedom. So the codes which you will have access to are codes where you, in addition to moving one particle, you also flip the spins, because the Hamiltonian can be spin dependent. In our case, we don't need to think of that, because the Hamiltonian is spin independent. So that means that when we are setting up the simulation, we don't need to deal with the spin degrees of freedom. However, the type of input, and this is something which differs from neural network code to neural network code, is what kind of inputs do you feed into the visible nodes? And you can feed in the single particle positions, but that will not obey if you only inform the network. So your trial wave function is now going to be a neural network. So we normally call this a neural quantum state. And instead of the Boltzmann distribution, which we set up, the trial wave function is now the neural network with all its parameters. So that means that you need to feed in to the network some information. And you could have some first attempt, and typically one of these, oops, sorry, I went a little bit too fast here. So one of the typical inputs you could feed in would be a trial wave function of this form here. And you would also inform the network with specific symmetries. And one of the standard symmetries which you want to obey is translational invariance. Also because many of the interactions actually depend only on the magnitude of the relative distance between two particles. So you could then feed in the relative distance, the coordinates, instead of just feeding in the positions of the particles, you could feed in the relative distance, the magnitude of the relative distance, and then you would have, for instance, the spin times spin, because sometimes you have an operator of this type here. And you would also feed in the single spin values. So these are some of the parameters you would feed into the network together with a beginning trial wave function. And then this is just to seed and start the network. And then the network will try to find the optimal representation of the trial wave function. You can also note that you can have an explicit, you could have an explicit dependence on the particle positions in the visible one-body features. And that would enforce some kind of translational invariance in the new features. So this can also be done because if you only include that one, you would not have translational invariance. So just skipping the single particle degrees of freedom as an input to the network is a way, when you now have the relative distance, of enforcing translational invariance. And then you can have linear transformation between the input layer, which are then given by these parameters V of I here, and this Vij, which are then defined as in the previous slide. So Vij contains these input parameters. And then the V of I are just the spin values. So we don't give the positions of the particles. We are more interested in keeping translation invariance, which is an important invariance. And that means that we will typically then have links between the first hidden layer and the visible layer, which then will be given by these parameters A and B, which then are respectively vectors and the matrices connecting the different nodes. And these would then contain the parameters to be trained in a neural network. As you can see, there are a lot of technicalities which need to be dealt with in order to set up a neural network code. And I hope you also see the reason why we don't do that in project 2, but we implement the Boltzmann machines, which are more straightforward due to the fact that we can reuse everything we had in project number 1. Now, I would also like to mention that there are actually many interesting neural network implementations which you can actually use and download. And one of these is Ferminet, which was developed by a collaboration between Google and Imperial College. And we actually have a former master student of us who is a PhD student at Imperial College and is actually working with Ferminet. And so this is something which you can actually download for free if you want to. And it's actually an implementation of the fermionic neural network for ab initio electronic structure calculations. So like this project here, if you wish to, you could actually download Ferminet and then try to use that one in order to implement a neural network. So that's fully possible if you wish to. So that's one option. Another option is to, let me just find back my notes here. Giuseppe Carleo, who introduced the Boltzmann machines, they have developed something which is called NetCat. And this is an alternative to Ferminet. And this is what they call a machine learning toolbox for quantum physics. And it contains a code to deal with neural quantum states. And it uses JAX in order to set up and speed up the code. And JAX allows you to implement automatic differentiation. At the same time, it has also inherited many of the number features in Python, which normally speeds up the code. And there are other codes or tools like OpenFermion and QTIP, and just take a look at them. I should say that JAX can be painful, and depending on your operating system, it may function out of the box, or you may actually have to struggle with it. And it took me a long time on my Mac OS to actually get JAX to work properly with the codes which I have. So these are implementations of neural networks which are very nice, and I would actually recommend to explore them. Take a look at these codes. And I actually wanted to, no, not that one. Yeah, there is a in the slides here. Here we are. So if you click on this link here, you will find a link to a very nice talk by Giuseppe Carleo, which actually goes through many of these details. So if we scroll down a little bit, you will find most of the way you can actually now learn the ground state of the system. So as you can see now, the quantity which we are dealing with is this expectation value. So we want to have the exact ground state. And we are calculating the gradients. So this is back to the same type of equations which we have been dealing with. And the quantities which we need to optimize are these integrals here, where this O here is actually the derivative of the trial wave function. And in this case, it has been written in terms of the parameters we want to optimize. And Z is then the position which we have. So this is essentially what we have been dealing with in project 1 and building up. And there's one thing which I wanted to say a little bit about, and this is the reason why I have brought up the slides of Carleo. This is a technicality which we have not discussed. And the reason for why we haven't discussed it is that sometimes it can be a little bit tricky to implement. But if you think back to your gradient descent, where you included the learning rate as a parameter which you tuned, or alternatively, you could have a stochastic gradient descent where you could have an adaptive way of training the learning rate. Another way of doing that is something which is called the Fisher information, which then is going to give us the second derivative of the expectation value of the energy in an approximative way. And this is a quantity which then the inverse of this quantity can actually be used to replace the learning rate. And this is something which has been very, very successful. And the basis for that is a paper by Sandro Sorella in Physical Review Letters back in '98. So that means that what you would have then, when you do the estimations, is that if you look now at the gradients or the parameters you're updating, the way we did that in project 1 and the way we are going to do that in project 2 here, and this is again mainly because of time limits, is to use this eta here as a parameter which we tune. Alternatively, if we do stochastic gradient descent, we can actually use a learning rate which has been optimized according to information about the gradient. But one possibility then is actually to estimate this Fisher information, which then can be used to compute the learning rate. And that works actually pretty well. There are several examples here, and you will see that the type of models which are implemented are models which deal with spins. And these are typical Ising type based models where you sum over the nearest neighbors. You have something which is called a J1, J2 models. If you go down, you will find the Heisenberg model. And this was the original paper by Troyer and Kaleo, where they computed the energy of the Heisenberg model, which is a spin-spin model. And that was implemented using just a binary Boltzmann machine, because you have actually only spin-up, spin-down systems. There are more implementations here, and you can look up the slides. You have the link to it. And there are possible implementations where people have actually implemented neuroquantum states, restricted Boltzmann machines. I don't remember what all these abbreviations PPR. This is density matrix renormalization group. VMC is a variational Monte Carlo, which you guys have implemented, etc., etc. So there are many interesting aspects in this talk, and I invite you to take a look at it. The link is the one which you find here. So if we then go back again, if you want to look more at the implementation and of a neural network, I wanted now just to quickly remind you, because this in a way favors a little bit those of you who have taken a course on machine learning and you've written your own neural network code. So if you want to venture into this, branch of deep learning applied to quantum mechanical systems, I would recommend doing so only if you have studied machine learning and you are somewhat familiar with neural networks. Neural networks are more difficult to implement in the sense that you need to set up a given number of hidden layers and nodes. You need to set up a given architecture. You need activation functions for the different nodes. We have hyperparameters which you can tune, which then are normally added with specific parameters multiplied with the norm of these parameters, and that can be an L2 norm or an L1 norm or a mix of various norms. You need different gradient algorithms, normally stochastic gradients, and ways to optimize this learning rate. And the learning rate is something in Monte Carlo calculations which is then replaced instead of using a adaptive momentum method or other ways to learn the learning rate adaptively. They are normally replaced by this Fisher entropy. And then one needs to implement the backpropagation algorithm and automatic differentiation for computing these updates of the various parameters. And then you need to find a cost function or so-called loss function which you want to optimize. So as I said, unless you're very, very familiar with neural networks, And the setup of these, I do not recommend taking this optional path. You have to see whether you want to do that or not. An obvious implementation is to take the codes from Ferminet or Netcat and try to implement those. They're actually very user-friendly. And that could be one way to actually solve the optional problem. If you want to study neural networks more, you can go to the lecture notes in Physics SDK 4155. And if you click on the link here and go to weeks 40 and 41, you will find the basic layout and setup of a neural network code. So there are several strategies you can use, and this depends on your interests. If you want to do the optional part, I would recommend using either Ferminet or Netcat, which are libraries which have been well tested and function very well. And you could then simply plug in the Hamiltonian which you are dealing with, which is the Hamiltonian, which consists of the harmonic oscillator and the Coulomb interaction, and then simply see if you can install that software. The codes which we have, on the other hand, if you now go back to the very first slide for today, you can now go into this link here, and you will find, first of all, you will find a main program, which is this neural network main, which is the one you would need to run. There is an unfinished function with a Coulomb potential. You will find the Metropolis algorithm, which is used when you evaluate the multidimensional integrals. So when you're calculating, and what makes everything difficult here is that you have to evaluate these integrals in order to calculate the gradients. So at every training stage in a neural network, you need to evaluate the gradients. And the gradients are given by expectation values. And when you calculate these expectation values, you're going to calculate these expectation values using a Monte Carlo sampling or Markov chain Monte Carlo, which means that you need a Metropolis algorithm. Here you will find ansatses for the neural wave function. And these codes have been actually fine-tuned to nuclear physics applications. And it contains a trial wave function for nuclear physics problems. It also contains a nuclear potential. This is tailored for nuclear many-body physics. There is the optimizer part. There is also a part which takes into account the spin degrees of freedom. So when you deal with the Coulomb interaction, you have no spin dependence, so you don't need this spin part. It implements JAX instead of autograd for automatic differentiation, and this can sometimes be a hassle to set up. But if you have JAX installed properly, then you will simply run this with Python neural network main .py here. So the let me just see here. Okay, so the there's a question in the chat here, which is a very good question. And let me just read the question here, actually. Are there physical reasons neural network is better than Boltzmann machines, like exact conservation of certain quantities or something like that? So there are several answers to that. So one has to do with the universal approximation theorem, which says that with one hidden layer, you can approximate any nonlinear function to a given precision with one hidden layer. And that means that you can then use the variational Monte Carlo machinery, but with a neural network as a trial wave function. And we've been running several calculations with neural networks, and we actually get better results than any other many-body method. So if you ask me about many-body methods, this is actually my field of expertise, and I've been programming and developing many different many-body methods. This could be many-body perturbation theory. It could be diagonalization methods, iterative methods like coupled cluster theory and so on, which are widely used in atomic, molecular, quantum chemistry, nuclear physics, condensed matter physics. I've been working on variational Monte Carlo methods, diffusion Monte Carlo methods, which are the methods which, if they converge, should actually represent in the best possible way the ground state. So what we have been shocked by is actually that these neural networks, they do a much better job than any other existing many-body method. And they actually give you a variational energy which is better than what you would get from diffusion Monte Carlo. So variational Monte Carlo depends always on your ansatz for the wave function. Here, with a neural network, you can actually tune the parameters by minimizing the energy and get really close to the best possible representation of the energies and thereby the wave function. So that's one aspect of it. A Boltzmann machine is less flexible in the sense that if you want to change the energy function, then you may actually end up with very complicated expressions for the marginal probabilities. You may actually have to sample from this multi-dimensional distribution. You may have to sample from them numerically. You may not be able to get an analytical expression. And that will clearly make the code less efficient. And then there is always a trade-off between whether using a neural network, which has many more parameters than a Boltzmann machine. So remember now that a Boltzmann machine has less parameters, as you've seen. So typically, the number of visible nodes are given by the number of particles you have, multiplied with the dimensionality. Whereas a neural network can have many hidden nodes. You're not limited by the dimensionality of the system. And it's much more flexible in the sense that you can use automatic differentiation when you're setting up the gradients. This can be a little bit more difficult with Boltzmann machines. On the other hand, Boltzmann machines don't use backpropagation in general. You have Boltzmann machines which do actually use backpropagation, but the way we have set it up, we don't need to use backpropagation. So there's a kind of trade-off between the complexity of the problem and how good a representation of the ground state you are interested in. If you want a rough representation, a Boltzmann machine does a good job. If you're dealing with spin systems, a Boltzmann machine is actually excellent because then you have binary outputs and inputs. So that's there's always a trade-off between the kind of systems. But for quantum mechanical system with continuous input variables plus spins, all implementations till now show that neural networks do a much better job in finding an optimal representation of the wave function. So it's a mix of both the numerical aspect, but also the kind of physics you can get out of the calculations. Now, there is more to this, so I'm sorry for going on a tangent here, but these are actually important aspects. When you train a neural network, the neural network is then the final wave function is then just represented by the parameters of the neural network, which means that you don't have a clear physical understanding of the trial wave function, or the wave function you end up with. When you set in a Boltzmann machine, then you have defined the way the trial wave function is going to look like, because it's defined by your ansatz for the Boltzmann machine. So you have a probability distribution where you can bake in a lot of your physics insights. And then clearly, if you have exact solutions like this Purcell-Teller approximation, then you have the possibility of actually comparing your Boltzmann machine with a exact solution. You can do the same with a neural network. So a neural network can then, in order to get physics insights about it, you would actually use that final wave function, which is represented by the biases and the weights in a complicated way. you would use that one to calculate other observables. And they may perhaps teach you about important physics correlations which are baked into the wave function you extract from a neural network. And then you can compare this with more traditional physics methods, like Hartree-Fock theory or other many-body methods, where you bake in actually a lot of physics insights. And then comparing the different so-called controlled methods, like Hartree-Fock theory, full configuration interaction theory, which is based on large-scale diagonalization, many-body perturbation theory, and so on, where you know what you're baking into the ansatz. Then you can compare the neural network and see if there are important correlations which are left out by the other methods. And I have to say that the results which we till now have gotten for this type of calculations have just been amazingly good. So I could actually, this is actually a very important question in the chat. I wanted to show you some results which we have from other types of calculations. And here it may be actually, yeah, so this is a calculation of which we did recently of the unitary Fermi gas. And the DMC calculations, the diffusion Monte Carlo calculation. So this is the best state-of-the-art calculation of the ground state energy for this unitary Fermi gas, calculated with this Pusch-Teller interaction I mentioned. And what you see here, this is actually the neural network with a Jastrow factor, a plane wave approximation to the single particle states and a Slater determinant, and the information about the relative distances and the magnitude of relative distances. So this was till recently seen as the benchmark calculation for these type of systems, whereas now with a neural network, you're actually getting energies which are below that. I could show you other types of results here. So let me just find, I have some other calculations here. This is a calculation of neutron star matter, which we did recently with neural networks. So let me just see if I can bring up the results here. And the calculations, if you look at the calculations which we have, so this is a calculation for neutron star matter. So this is pure neutrons in dense matter and at low densities. And in that case, what you can see now is that the calculations here, so this constraint calculation is actually not correct. It's not obeying the variational principle. So the best one is actually the one you see here. This is the best diffusion Monte Carlo calculation. This is what you would get with a variational Monte Carlo calculation. And for those of you who are more familiar with many-body physics, this would be a mean field result. So you see there's a big jump between that one and variational Monte Carlo. And then our neural network with basically almost no information except the anti-symmetry and the relative distances and spins is actually giving results which are on par with the theoretical benchmark which exists nowadays, which is given by diffusion Monte Carlo calculations. So the results have been amazingly good, I should say. And I think this is a very, very interesting avenue to explore. And there's a lot of research activity going on. So if we go back a little bit to the slides this week, let me just bring in the slides which we had. Here we are. So if you wish to take a look into the codes here, feel free to do that. But then I would, if you wish to implement a neural network, what I would recommend is either to download Netcat or to download Ferminet and try to implement that one for the for project number 2 here, if you want to do that. As I said in the beginning, I discourage a little bit the implementation of that because that can quickly become time consuming. and the Boltzmann machines contain already a lot of the basics of deep generative models and many of the basic features of setting up a neural network. Okay, let me take a break here.